Hello, friends. Today we're on to topic 2.11, and we're looking at some key characteristics of logarithmic functions, still looking at them as the inverse of exponential functions. And let's begin. So again, the general term of logarithmic function looks like this, right? A log base b of x, where again, b is bigger than 0, a cannot be 0, and b cannot be 1. In general, the domain is from 0 to infinity, right? We can't have negative numbers. And the range is from negative infinity all the way to infinity. Right? And so this is the general shape, right? If a is less than 0, really all you're doing is you're reflecting the function over the horizontal axis. Right? Putting a negative in front gives you that flipping transformation. And then increasing versus decreasing. So logarithmic functions are always increasing or always decreasing. They never switch from increasing to decreasing or something like that. And so there are no local extrema or even absolute extrema, right? They go to infinity vertically up and down. Concave up versus concave down, because of the way they are, right? They're always concave up or always concave down. Right? Each individual function is either concave up or concave down. There are no points of inflection where it switches from being concave up to concave down or vice versa. The end behavior. Okay, so what happens is the as the input increases without bound, the output values will also increase or decrease without bound. Right? There are no horizontal asymptotes here. However, they can have a vertical asymptote. Right? They will have a vertical asymptote. Usually at x equals 0. Again, unless you're adding 1 or there's something like that, you're having some horizontal translation. But in general, based on the general form of the function, there is a vertical asymptote at 0. And so the description would look something like this, right? The limit as x approaches 0 from the right, right? That means you're approaching 0 from the right. So kind of moving to the left towards 0. X equals either positive or negative infinity. It will be one or the other. It's not going to be both. And then the limit as x approaches positive infinity of the logarithmic function is positive or negative infinity. And it'll be the opposite, right? So if the limit as x approaches 0 is positive infinity, the limit as x approaches infinity will be negative infinity. Okay, so let's look at some examples. I apologize, the formatting didn't come out right the first time here. But just in example 1a, based on the shape of that graph, the limit as x approaches 0 from the right is negative infinity. So I'll write that in here. And then on the right, so we write this as, notice, so as we're going out to the right, it's going up. And so it's going to increase without bound. So the limit as x approaches positive infinity of f of x equals positive infinity. Right? Goes up. And then it's going to be the reverse for h of x, right? Because it's flipped. So we're going to get positive infinity as we get closer to 0, negative infinity as the function goes out to infinity. So the limit as x approaches 0 from the right of h of x is infinity. And then the limit as x approaches infinity of h of x is negative infinity. Okay, very simple. Now we're on to c. So we're looking at g of x. So what does g of x look like? 2 times log base 3 of x. So a is not negative, a is positive here. That means that this function is going to look like what we could kind of call our normal function coming up across like that. Right. That means then that on the left, right, as it's approaching the limit as g of x, as x approaches 0 from the right of g of x equals negative infinity. And then the limit as x approaches infinity of g of x equals positive infinity. on to example 2. It says determine if the logarithmic function is increasing or decreasing and concave up or concave down. Okay. Well, the function, again, the function, you could just think of it as the output, right? So as we're going from left to right, the output values are going down. And so this is a decreasing function. And as I look at it, I can just recognize that it's concave up, right? Because it's kind of bowl-shaped up. If there was a curve and you're going into, right? But you can think of it this way too. What's happening with the slope? So if I were to draw a line that represented the slope of the tangent, right? So something like this, it would be almost vertical here. And then as I go along, notice that it's getting flatter, right? So I'm trying to keep this line tangent. So it's kind of getting flatter. So it's going from more negative to more positive, right? The right side of that line is kind of tipping up. And so we would say that this is concave up, right? Because the rate is increasing. Okay, next one. Concave up or concave down. Here the rate is decreasing. If I do that same thing with the line, kind of have the slope of the tangent line, right? And then I run along going to the right. I have to get it flatter and flatter. So the arrow is pointing, or it's moving, more and more down as I go to the right. So the rate is decreasing. It looks like this. So that's concave down, but the function is increasing. As I move from left to right, the output values are going up. Okay, again, the formatting here is a little off. So h of x equals -4 log base 6 of x. What does this look like? Notice that a is negative in this case. And so that means that it's going to be going down. It's going to look like example A. So it'll look like that kind of thing. And since it looks like example A, I already went through the reasoning for that. It's concave up and it's decreasing. Okay, when we get to example 3, all we're doing is trying to figure out the value of k. And the key thing for doing this is remembering that when it comes to exponential functions, the output changes additively, the input changes multiplicatively, right? The inverse of what happens with exponential functions. So in logarithmic functions, we can see the first example, f of x, right? The output is changing additively, but the input should be changing multiplicatively. And so this is a difference of, right? It's the difference of 1. We don't know what the difference is between 2 and k. The difference between 8 and 16 is 8. So this could be a difference of 2, difference of 4. So it's changing multiplicatively by multiplying by 2. So in that case, then 2 times 2 would be 4, and then 4 times 2 would be 8, and that makes sense. Okay, g of x. Again, the output is changing additively, so the input should be changing multiplicatively. It's a logarithmic function because they've told us that. And so what I notice is that 6 to 18, that's a difference of 12, but I can think of it also as 6 times 3 is 18, right? So this is times 3. Let's see if that pattern continues, just to be checking what we're doing here. 18 times 3 is 54. Yep, that works. And then 54 times 3 is 162. So that means some number times 3 is equal to 6. So that's got to be 2. K is equal to 2 in this case. Okay, h of x. Again, the output's changing additively. X is changing multiplicatively. So this is a difference of 1. And then I have a difference of 2. Come on in. What's up? Come on in. Oh, no problem. Okay. Yep, no problem. Okay, and so from 4 to 5 and then 5 to 7, it looks like the difference is being multiplied by 2. So let's try that again. So then if I try a difference of 4, that would give me 11, right? So plus 4. And then from here to here would be 11 to 19 would be plus 8. So it works, right? That means that we have a base here of 2. But again, all I'm looking at here is trying to figure out what k is. All right, now this one, it actually gives it to us in exponential form. E to the negative 2, e, and then k. So k is going to be e to the something power, right? It's being multiplied by something. And so e to the negative 2. So if I add, so if I multiply by e squared, or yeah, if I multiply by 3e squared, that wouldn't work because that would give me e to the 0. So this is actually, right, e to the 1. Don't forget there's a little hidden 1 there. So what makes sense here is from negative 2 to 1. So then I would end up with e to the 4th power, right? Because this is changing by, e to the 3rd. And then e to the 7th, this is also multiplying by e to the 3rd, right? Times multiplying by. And so again, e to the, so e to the 1st, this would be, again, times e to the 3rd. Let's see if that works. So this would give us e to the 4th, right? So then that times e to the 3rd, that also works. It gives me e to the 7th. Right? So I'm just looking for the pattern and trying to find what's that missing value there. Okay. And so here the base obviously is e. And so this would be, again, the way that we write a logarithm where the base is e was ln, right, or natural log. Example 4 wants us to find the domain and range of the following logarithmic functions. And so what I have here initially in A, it's just kind of a normal logarithmic function, the regular form. And so the domain is going to be 0 to infinity, and the range is going to be negative infinity to infinity. Normal domain and range for the basic formula, the basic function. In B, it's negative, right? A is negative in this case, negative 5. So that means the whole thing is flipped, but the domain and range still stay the same because of that. However, notice that I have x minus 3 in the function, right? In the input in that function. And so what happens here is that there's a shift. There's a horizontal translation that does the opposite of what it looks like because it's in there. And so the domain, right, this whole thing is going to be shifted to the right, 3, right? Again, it does the opposite of what it looks like. So the domain is 3 comma infinity, and the range is negative infinity to infinity. Okay. And then the last one, um, again, I have a horizontal translation because I have 2x plus 3 in there. Again, I apologize for the formatting. And so the horizontal translation is to the left by a factor of 3 over 2. Okay, and so the domain is going to be negative 3 over 2 to infinity, and the range is going to be negative infinity to infinity. Okay, so looking at some of the basic characteristics, domain and range, and then filling in tables for logarithmic functions. Again, thanks for watching. Don't forget to subscribe.